Hi, and welcome to the Differential Equations lectures here on Educator.com. My name is Will Murray, and I'm very glad that you're going to be joining me. Today we're going to start right away with linear equations. That's kind of the first topic of differential equations. There's a special algorithm that we're going to learn to solve them. So let's jump right in. So we're going to learn how to solve linear differential equations. And the way you recognize a linear differential equation is that you can put it in this form: y prime of x plus p of x times y of x equals q of x. Now, you might be using different variables, like you might have a t instead of the x. That's okay. The methods are exactly the same. I wanted to make a couple notes about the form here, that the word linear doesn't necessarily mean what you think it would mean. You can still have lots of functions in here that are not linear. Linear means that we think of y and y prime as the variables, not x and y, but you think of y and y prime as the variables. And you think of the p of x and the q of x, even though they're functions of x, you think of those as being the coefficients. So they might be something like cosine of x or e to the x or anything like that. But the point is, you think of those as being coefficients. And so if you look at this equation, the linear form is y prime plus p times y is equal to q. And so if you think of y and y prime as the variables, and if you think of p and q as being coefficients, then what you have there is a linear function in terms of y prime and y. And that's what we mean when we talk about a linear differential equation. Another note I wanted to make here is that if you have something in front of the y prime of x, if you have a coefficient right here, the solution method that we're going to learn on the next slide doesn't work until you get rid of that coefficient. So what you have to do is divide both sides by that coefficient to get rid of it and give yourself a nice clean slate, clean y prime of x with no extra coefficient. So we'll make sure to divide any coefficient here in front of the y prime before we start the algorithm that we're going to learn on the next slide. Divide away any coefficient here first. So that's a very common mistake that some of my own students make when I teach them differential equations. Is I'll give them an equation where I have a coefficient here, and they'll go through and they'll use the algorithm that we're about to learn, but it won't work because they forget to divide that coefficient away. So let's start to learn that algorithm. So how you solve linear equations is you calculate something called the integrating factor, which means you look at the coefficient of the y of x, which is the p. So you look at the p of x and you integrate it. So you take its integral and then you raise e to that power. So it's e to the integral of p of x. And then so we call that the integrating factor I of x. And we multiply that by both sides. So a lot of times this makes the equation get a lot more complicated. So let me show you why we would want to do that. So what we have here on the left-hand side, we'll have I of x times y prime. And then here we have y times a very large mess. But what this mess turns out to be is the derivative of I of x. Because remember that when you take the derivative of e to something, the derivative of e to the u, so d by du of e to the u, is just e to the u times the derivative of u. Let me just write d of e to the u is e to the u du. And so what we have here is, that's the e to the u right there, e to the u, and then this is the derivative of that, because that's the derivative of u, because the derivative of the integral of p of x is equal to the original p of x. That sounds a little complicated. I think it'll make a lot more sense after we jump into some examples, so don't worry about it too much right now. The important thing is to notice that we have I of x times y prime and I prime of x times y. And so that is exactly, if I write it this way, iy prime plus I prime y, that's exactly what we would have gotten if we had taken the derivative of I times y using the product rule. So we're really exploiting the product rule from Calculus 1 to solve this kind of differential equation. And so what that means is you can integrate both sides. When you integrate both sides, you're going to get IY on the left and whatever you get on the right. And then the point is we're going to take it from there and we're going to solve for Y. I think this will make more sense after we do some examples. So if it's still a little fuzzy right now, don't worry. We'll work through some examples together and you'll definitely get the hang of it. As I said on the previous slide, after you integrate both sides, you're going to get I of x times y of x times y on the left. Remember I said you get IY on the left. And you'll get whatever you get by doing this integration on the right. And you can then solve for y of x by dividing both sides by this I of x. So that's the plan for these differential equations. After we do some examples, I think it'll be a lot more clear. So there's a couple notes that I wanted to make before we jump into some examples. One very common mistake, let me just remind you of the original form we're solving here. Y prime plus P of x y is equal to Q of x. So that's the form that we're solving. Now, if P of x is negative, meaning if you have a negative sign right there, you want to make sure to include that when you're finding I of x. That's a very common mistake that my students often make when I'm teaching differential equations. Remember that the integrating factor I of x is e to the integral of P of x dx. Well, if there's a negative sign here, then that's part of the P of x and you have to include it in here. But a lot of people just don't notice that negative sign. They forget to include it. And trust me, that'll really ruin all the calculations after that. So make sure you include the negative sign. Another related mistake that is very common is resolving this e to the integral. A lot of times when you take the integral, you get the natural log of something. And so my students sometimes see e to the negative natural log of something. I wrote cucumber here. E to the negative natural log of cucumber. And my students will say, oh, I know that e and natural log cancel each other out, so e to the negative natural log of cucumber is just negative cucumber. That's wrong, and let me show you why it's wrong. If you have e to the negative natural log of cucumber, then that's really the same. Remember the rules of natural logs as e to the natural log of cucumber to the negative 1 power. Remember, the rules of natural logs say you take numbers on the outside and they turn into exponents. So that's e to the natural log of cucumber to the negative 1, which is 1 over cucumber, which is just 1 over cucumber. So that's a very common mistake that I see students make all the time. They want to cancel e and natural log, but they do it so quickly that they don't notice that that negative sign is in there, and they just try to pull that negative sign outside. It doesn't work. This is how it works out as 1 over cucumber. You got to be really careful about stuff like that. Another note that I wanted to make is when you're doing this integral to find the integrating factor, e to the integral of P of x, you can leave off the constant there. It doesn't really matter if you add an arbitrary constant or not, so might as well just leave it off. So you don't have to worry about the constant there. However, later on in the problem, when you're integrating both sides of the equation, the constant is very important. I can't stress this enough. I'm going to highlight that part right there. The constant is very important when you're integrating both sides of the equation. And it's also very important that you do it exactly at the moment when you do the integration. When you do the integration, that's when you have to add the constant. The reason you have to be so careful about that is that after you do the integration, you usually have to do a couple more steps of algebra to solve for y. And you have to keep track of that constant as you go through those algebraic steps. Sometimes that constant gets tangled up in the equation. So this is a very big difference from when you first learned how to do integrals back in Calculus 2. In Calculus, well, even in Calculus 1 or Calculus 2, you could do the whole problem and then just tack on an arbitrary constant at the end. You could even do 5 problems, and then at the end you just go back and put a plus c on every single one of them. That does not work in differential equations. You have to add the constant in the middle of the problem when you do the integration step, and then keep track of it after that. So if you just go back at the end and tack on a constant at the end, you will get the wrong answer. So I think you'll see in some examples how that plays out, but let's just remember to add the constant exactly when we do the integration. So let's jump in with an example now. We're going to find the general solution to the following differential equation. Y prime plus xy is equal to x cubed. So let's remember the strategy here. Our generic form for a linear differential equation is y prime plus p of xy is equal to q of x. And that's what we've got here. We've got y prime plus a function times y is equal to another function. And remember the strategy here is to find the integrating factor. I of x is equal to e to the integral of p of x dx. That's always our strategy for linear differential equations. In this case, the p of x is that x right there. So that's the p. And so we have to do e to the integral of x dx. And that's just e to the x squared over 2. The integral of x is x squared over 2. Remember that when you're doing this integration to find I of x, you don't have to worry about a constant here. So no plus c necessary at this integration. Oops, I'm misspelling necessary here. Necessary. No plus c necessary at this step. Later on, there's going to be another step where we do integration, and at that point, it's going to be absolutely crucial to include the plus c. So what we do with this integrating factor is we multiply it by both sides of the equation. So I'm going to multiply e to the x squared over 2 times y prime plus, I'm going to write this in the middle, x e to the x squared over 2 times y is equal to x cubed e to the x squared over 2. Now, the whole point of these linear equations and this integrating factor strategy is that this left-hand side is supposed to be the derivative of y times I of x using the product rule. So let's look at that. I'm saying that this is the derivative of y times e to the x squared over 2. That was our I of x. It's supposed to be the derivative of that using the product rule. And it's always good to check at this step that it worked. So if we took the derivative of y e to the x squared over 2, we get y prime e to the x squared over 2. And then y times the derivative of e to the x squared over 2, which is e to the x squared over 2 times x. So that right there is I of x, I prime of x, and that right there is I of x. So we do get something that looks like the aftermath of the product rule. So that kind of confirms that we did our work correctly. And this is still equal to x cubed e to the x squared over 2. Now, we're going to have to solve this, and the way we're going to do that is by integrating both sides. And so if I integrate the left-hand side, I had a derivative, so I'm going to go y e to the x squared over 2. That's by integrating both sides, is equal to the integral of x cubed e to the x squared over 2 dx. And so now I have to solve that integral on the right. I think I'm going to take another slide to do that because that's not the easiest integral in the world. So let me just recap what happened on this slide here. We started out with this linear differential equation in this form, y prime plus p of xy is equal to q of x. And our strategy for linear differential equations is to form this integrating factor where you do e to the integral of p of x. The p of x is just x, and its integral is x squared over 2. We don't need to add a constant for that integral. And then we multiply that by both sides, so I multiplied that by all three terms here. And the point is that that makes the left-hand side into I of x times y prime plus I prime of x times y. So we get a product rule going on, and that's the derivative of y times I of x. And so if we integrate both sides, on the left-hand side, we just get y times I of x. On the right-hand side, we have an integral that we still need to solve. So that's what I'm going to carry over onto the next slide, and we'll keep going there. Okay, so we're still have a couple steps to go on example 1 here. We had, on the previous slide, we had y times e to the x squared over 2 was equal to the integral of x cubed e to the x squared over 2 dx, and we have to solve that integral. And what I'm going to do is make a little substitution here. I'm going to do u is equal to x squared over 2, and then my du would be equal to 2x over 2, so just x dx. And so I'm going to write this integral as, I think I'm going to take that x cubed and write it as x squared, and that'll give me another x to put over here with the dx, and this is e to the u, and now x squared is 2 times u, so I'm going to pull a 2 out here and change that x squared to a u, e to the u, and now x dx is du. And I still need to do integration by parts to solve u e to the u. So let me set up integration by parts to solve u e to the u. I have a little shorthand technique for integration by parts. It's called tabular integration. I taught this on some earlier Educator videos for the Calculus 2 or the Calculus BC series. So if you go back and look at those Calculus BC lectures here on Educator.com, you'll see a section for integration by parts, and that's where I taught this section on this trick for tabular integration, to do integration by parts quickly. What I'm going to do is take derivatives of u. So the derivative of u is 1, and the derivative of 1 is 0. And then I'm going to take integrals of e to the u, so that's just e to the u, and then e to the u again. And then I write little diagonal lines here and put alternating signs, positive, negative, down the diagonal lines. And then I just multiply down the diagonal lines. I still have a 2 on the outside. And I have u e to the u minus e to the u. And that's still equal to y e to the x squared over 2. Now, I want to really emphasize something right here. This is the step where I did the integration. So this is where I have to put a plus c. That's really crucial here. I put a plus c right now. Let me really emphasize that. Must add c. You can't just add c at the end. So we must add plus c when we do the integration, and not earlier and not later. When we do the integration. No earlier, no later. And the reason we have to do it then is because the next step is to solve for y, and that's going to involve some algebra that's going to change the equation around a little bit. And the c is going to get tangled up in with that algebra, and we need to let that happen. We can't just tack it on at the very end when we're all done. So what we have here is, I think I need to get things back in terms of x. So 2 times u is x squared over 2, e to the x squared over 2, minus e to the x squared over 2, plus c. And I would like to divide both sides by e to the x squared over 2 because I want to solve for y on the left. So if I divide both sides by e to the x squared over 2, I'm just going to get 2 times, in the inside here, x squared over 2 minus 1 plus c. Now, dividing by e to the x squared over 2 is the same as multiplying by e to the negative x squared over 2. So I get y is equal to, if I distribute that 2, I get x squared minus 2 plus a constant times e to the negative x squared over 2. That's as far as I can take this one, so I'm going to stop there. That's called the general solution right there. The general solution always has an arbitrary constant somewhere in it. And the way you would find the value of that arbitrary constant would be to use initial conditions if you were given an initial condition. In this case, we weren't given an initial condition, so we can't find the arbitrary constant. So use initial condition. If given. In this case, we weren't given one. To find the value of C, to find the exact value of C. And if you don't have an initial condition, then you just leave it in terms of a general solution like I did here. So what we really found here is the general solution. General solution. So that's as far as we can take it on this one. The next example will have an initial condition, and you'll see how we'll plug that in at the end to find the value of C. But in the meantime, let's go back over what happened with this example. This is the integral that I got from the previous slide. So this is all work that we did on the previous slide. You can check back at the previous slide if you don't remember where this all came from. So we solved it to the point of getting y e to the x squared over 2 is equal to this integral. And this is a slightly messy integral, so I made a little substitution. U equals x squared over 2. Of course, I had to do my du as well. And then, because I had an x cubed here, I factored that into x squared and an x. And the point of that was I wanted to segregate out an x to be my du here. So that x dx became the du. That x squared is 2 times u, so that gave me a 2 and a u here. And we have e to the u. And now, just to do e to the u, I have to do a little integration by parts problem. And I have this tabular integration method that I covered back in my lectures in the Calculus BC section here on Educator.com. So you do derivatives of u, so these are derivatives. And then integrals of e to the u, we do integrals. You cross multiply them along with these little alternating signs, plus, minus, plus. And so we get u e to the u minus e to the u. Substitute back in u as x squared over 2. And then we're trying to solve for y. So that means I have to divide both sides by e to the x squared over 2. So that's what I did here. I canceled off my e to the x squared over 2 here and here. Now with the c, I have to multiply by e to the negative x squared over 2. That's the same as dividing by e to the x squared over 2. And then I just distributed this 2, canceled off the 1/2, and we got x squared minus 2 plus c e to the negative x squared over 2. At this point, if you had an initial condition, you would use it now to figure out the value of that arbitrary constant. If you don't have an initial condition, which is what happened with this problem, you just stop and you say, that's your general solution. So in example 2, we have to find the solution to the following initial value problem. Cosine xy prime plus sine xy is equal to cosine of the 5th x sine x, and then the initial condition is y of 0 is equal to 2. Now let me remind you the format for a linear differential equation. It has to be in this form, y prime plus p of xy is equal to q of x. It's got to be in that form. In particular, it's not allowed to have any coefficient in front of the y prime. Here we do have a coefficient in front of the y prime. We got a cosine x. So what we're going to do is just divide both sides by that cosine x to get it into the required linear form. So we get y prime. So we're going to divide by this. Got to divide both sides here. So I get y prime plus sine x over cosine x y. Now, if I have cosine of the 5th on the right and I divide by 1 cosine, it'll go down to cosine into the 4th x, sine x. Not going to worry about the initial condition because paradoxically, you use the initial condition at the very end of the problem. So we won't worry about that for quite a long time. Now, let's remember our general strategy for linear differential equations, which is that you use this integrating factor, I of x, is equal to e to the integral of p of x dx. So in this case, my p of x is the coefficient of y, so that's p of x right there. By the way, you could rewrite this as tangent of x if you wanted. I don't think that's going to be useful for what's coming up, so I don't think there's any particular benefit to writing it as tangent of x, but it wouldn't be wrong. So that's the p of x. p of x right there. And so what we get here is the integrating factor, I of x, is equal to e to the integral of p of x. So e to the integral of sine x over cosine x dx. And so in order to integrate that, I think I want to do a little substitution. Of course, you could remember what the integral of tangent x is, so certainly that would be great if you did remember it. But I'm not going to assume that you remember it because we're going to solve that just with a little substitution. We're going to use u is equal to cosine x, and then du would be negative sine x dx. So this is e to the integral of, well, there's a negative sign there, so I have to put negative du. So du is sine x dx with a negative. Cosine x is u. So e to the negative integral of du over u, and that's e to the negative natural log of u, which is e to the negative natural log of u is cosine x. Now, a couple points to mention here. First is that you don't have to add the arbitrary constant when you're finding the integrating factor. So you can omit the plus c at this point. It's okay. Later on, it'll be very important to add on that arbitrary constant when we do another step of integration later. But here you don't have to worry about it. Next thing to be very careful about is, let me write this in red to show that it's wrong. A lot of my students would look at this and say this is equal to, e to the negative natural log of cosine x. The e and the natural log cancel, so this is just negative cosine x. That's wrong. So I want to make it clear that you don't want to do that. Instead, what you want to do is you write that as e to the natural log of cosine x to the negative 1. Remember, that negative becomes an exponent, so that's just cosine x to the negative 1, which is 1 over cosine x. And that's the actual integrating factor. So that's also the same as secant x. That's the integrating factor, not negative cosine x. That would have really steered you wrong. So let me go back to the original equation here. We have y prime plus, I think I am going to write it as tangent x. Tan xy is equal to cosine to the 4th x sine x. And remember, the point of the integrating factor is you're going to multiply both sides by that integrating factor. So we'll multiply both sides by secant x, and we'll get secant x y prime plus secant x tan x y is equal to, now remember, secant x is 1 over cosine x, so we're really dividing by a cosine x. So we'll go down now to cosine cubed x sine x. And the point of that is that the left-hand side is exactly what you would have gotten if you had taken the derivative of secant x times y using the product rule. Remember, the product rule says derivative of one times the derivative of the other times the one. And so that would have given us secant x times y prime. And then the derivative of secant is secant tangent times y. So that's exactly what we would have gotten via the product rule had we taken the derivative of secant x times y. The product rule is what works, and this is supposed to work for every linear differential equation. That's the whole point of this. This is still equal to cosine cubed x sine x. And so we're going to integrate both sides here. And on the left, that means we're going to get secant x just times y without a derivative, because we integrated a derivative. We just get back to the original function. On the right, we still have the integral of cosine cubed x sine x dx, and we'll have to wrestle with that integral. I think I'm going to go ahead and work that out on the next slide. So let me remind you what happened on this slide. We had this differential equation here, but it's not quite in perfect linear form, and the reason it's not in perfect linear form is because of this coefficient in front of the y prime. So we're not supposed to have anything in front of the y prime except for a 1. So we have to divide away by that cosine x. So that's why I divided the cosine x. In front of the y, I got sine x over cosine x. And cosine fifth went down to cosine to the fourth because I divided by cosine. So we got this new form of the differential equation. That is in linear form. And so we can use our generic linear strategy, which is to use this integrating factor, which means you look at the p of x, there's my p of x there, and you try to integrate it, and you raise e to that power. Now to integrate sine x over cosine x, I use a little u substitution. U equals cosine, du equals negative sine. So we got negative du over u, which gave me negative natural log of u. I didn't have to add a plus c here. That's going to come later on. The negative natural log of u substitutes back to negative natural log of cosine of x. And it's very tempting at this point, and it's something that students often do, is to try to cancel the e and the natural log. But it doesn't work because of that negative in between them. You got to turn that negative into an exponent first, then you can cancel off the e and the natural log, and you get 1 over cosine x, or secant x, as your integrating factor. So the point of that was you multiply both sides of the equation by that integrating factor. That's what I'm doing here. On the left, I get secant x times y prime plus secant x tangent x times y. And the point of that is that it's the derivative of secant x times y using the product rule. If you use the product rule and expand this out, you get exactly these two complicated terms. On the right-hand side, when I multiply by secant x, that's like dividing by cosine x, so I got cosine cubed x times sine x, and I'm still stuck with that. I still have to integrate that. That's what we're going to jump over onto the next slide and keep going. So on the previous slide, we got it down to secant x times y was equal to the integral of cosine cubed x times sine of x. This is all coming from the previous slide here, dx. And so I have to solve this integral on the right. I'm going to use a little substitution now. U equals cosine x. And my du, you always have to find the du when you do a substitution. Du would then be negative sine x dx. And so I've got the integral of u cubed. And that sine x should be negative, so I'm going to put a negative out here. Negative du. And so that's negative u to the fourth, using the power rule, over 4. Now, I just did my integration. Now is when I have to add a constant. So it's very important that I add it right now. Negative u to the fourth over 4, which is negative 1/4 times changing u back into cosine x. This is cosine to the fourth x plus a constant. This is still equal to secant x times y. Now I want to solve for y, so I'm going to multiply, well, I want to divide both sides by secant x. That's the same as multiplying by cosine x. So I'll multiply both sides by cosine x to cancel off my secant. And so on the left I'll just get y. On the right I'll get negative 1/4 cosine to the fifth x now, plus c times cosine x. That's why we had to add that c, is because the algebra that we do afterwards to solve for y starts to tangle up the c into the equation here. Now, if we didn't have an initial condition, we'd be done, because what we found right here was the general solution. But this time we have an initial condition. Y of 0 is equal to 2, so we're going to use that here. So y of 0 is equal to 2. I'm going to plug in 2 for y, and 0 for x, minus 1/4 cosine to the fifth of 0 plus c times cosine of 0. Cosine of 0 is 1, so 2 is equal to minus 1/4 plus c, and my c, if I move that 1/4 over the other side, 2 plus 1/4 is 9/4. And so I'm going to plug that back into my general solution right there. And so I get y is equal to negative 1/4 cosine to the fifth x plus 9/4, not by itself, but 9/4 cosine x. And that is my complete solution to the original initial value problem. Solves the differential equation, and it matches the initial condition. So let me remind you of the steps here. it was on the previous slide where we got this down to the point of having secant x times y is equal to the integral of cosine cubed x sine x. And then we used, to solve that integral, we use a little u substitution. U equals cosine x, du equals negative sine x. Because of that negative, that's where that negative comes from. And so then we get an easy integral of u cubed. So that gives me u to the fourth plus a constant. And on the left-hand side, I have this secant x times y. To solve for y, I'm going to divide by secant x. That's the same as multiplying by cosine x. So I multiply both sides by cosine x. So that's why this fourth became a fifth here, and the c got multiplied by cosine x. And now I use my initial condition here. Plug in 0 for x and 2 for y. So 2 is negative 1/4 cosine to the fifth of 0 plus c cosine of 0. Cosine of 0 is 1. And so 2 is equal to negative 1/4 plus a constant. Move the 1/4 over to the other side. I get c is equal to 9/4. And then I take that and I plug it back in to my general solution right here. And so that's where I get y is equal to negative 1/4 cosine to the fifth x plus 9/4 cosine x. In example 3, we're given a linear differential equation, and we're just asked to find the integrating factor. So we don't have to solve this one all the way through. So what we have to do here is just find the integrating factor. Remember, the general form for linear differential equations, though, is y prime plus p of x y is equal to q of x. In particular, you're not allowed to have anything in front of the y prime, any coefficient here. We do have a coefficient right here, x plus 1. So what I'm going to do is divide that away. I'm going to go y prime minus 1 over x plus 1, y, is equal to 1 over x plus 1 times sine x. 1 over x plus 1 times sine x. Now, the way you find the integrating factor, you do e to the integral of p of x dx. And the p of x here is whatever's in front of the y. And the key thing here is that you not forget the negative sign. The negative is part of it. So that's all p of x right there. P of x. And so this is e to the integral of negative 1 over x plus 1 dx. Now, that's e to the negative. Now, the integral of 1 over x plus 1 is just natural log of x plus 1. And remember, you don't have to worry about a constant when you're finding the integrating factor. Now, you can't cancel the e and the natural log because there's a negative sign in between them. So you got to write e to the natural log of x plus 1 to the negative 1. Now you can cancel the e and the natural log. So you get x plus 1 to the negative 1. And so that's just the same as 1 over x plus 1. And that's all we were asked to do for this example, is to find that integrating factor, and we found it, so we're done. So let me go over those steps one more time. The key thing here is I remembered the generic form for a linear differential equation. It's got to be y prime plus p of x y is equal to q of x. And that only works if the coefficient of y prime is 1. So here the coefficient of y prime was x plus 1. So I just divided away. I just divided both sides by that. And so that's how I got it into this form. Y prime minus 1 over x plus 1y is equal to 1 over x plus 1 times sine x. And now whatever's in front of the y is your p of x, but you got to include that negative sign. So I plug that into my generic integrating factor formula, including the negative sign, and that's an easy integral. The integral of 1 over x plus 1 is just natural log of x plus 1, but there's still that negative sign, so I can't cancel the e and the natural log yet. So instead I make that negative 1 into an exponent, and now I can cancel the e and the natural log. And so I end up with just 1 over x plus 1. In example 4, we're given the linear differential equation sine x y prime minus cosine x y is equal to x squared. And we want to find the integrating factor I of x. So again, let's remember our generic form for a linear differential equation. Y prime plus p of x y is equal to q of x. In particular, you can't have any coefficient in front of the y prime. So we've got this sine x here, so I've got to get rid of it by dividing it away. So I'll divide that and get y prime minus cosine x over sine x y is equal to x squared over sine x. And now I can use my form for the integrating factor, which is I of x is equal to e to the integral of p of x dx. And that p of x means whatever is in front of the y, but it includes the negative sign. So go ahead and put that in there. E to the negative cosine x over sine x dx. And to solve that integral, of course I could think of that as cotangent of x, but I don't think that's particularly useful here. So what I'm going to do is a little substitution. I'm going to use u equals sine x. U equals sine x. And so du is negative cosine x dx. And so I've got e to... du is just positive cosine x because the derivative of sine is positive cosine. I was kind of looking ahead at my negative sign there, but the derivative of sine is just positive cosine. So we have e to the negative integral of du over u. And so that's e to the, well, that negative sign just stays there, but the integral of du over u is negative natural log of u. And so that's e to the negative natural log of u was sine x. And again, we got this negative sign in between the e and the natural log, so I can't cancel. A lot of students are very tempted to cancel the e and the natural log and just say, oh, that's negative sine x, but it's not. So instead you use that negative and make it into an exponent. So that's e to the natural log of sine x to the negative 1. And so now you can cancel the e and the natural log. You get sine x to the negative 1 power. And so that's equal to 1 over sine x, which is cosecant of x. By the way, sine x to the negative 1 is not the same as arc sine or inverse sine x. This is really means, that's really an exponent, so it really means 1 over sine x. Be very careful here that this is not the same as sine negative 1 of x or arc sine x. Doesn't mean the same thing as either one of those. That's another frequent mistake that students make. So we're done here because we were just asked to find I of x and we found it. So let me recap the steps there. We wanted to get the equation into linear form. Y prime plus p of x y is equal to q of x. So in order to do that, I had to divide away this sine of x. So I divided away, I get y prime minus cosine over sine y is equal to x squared over sine x. And then the integrating factor, you do e to the integral of p of x dx, where the p of x is whatever's found in front of the y, and you got to include that negative sign there. So that's all p of x. To do that integral, I did a little substitution. U equals sine x, du equals cosine x dx. So we get negative du over u, which is negative natural log of u. And so that's substituting back, that's negative natural log of sine x. Now I can't cancel the e and the natural log yet because I've still got that negative sign in between them. So I make that an exponent. And now I can cancel the e and the natural log, and I just get sine x raised to the negative 1 power. That's not the same as inverse sine. That's not the same as arc sine. It's really sine x raised to the negative 1 power. And so that's 1 over sine x, which is cosecant of x. So in example 5, we've got to solve the following initial value problem. T plus 1y prime minus 3y is equal to t, and y of 1 is equal to 2. So let's go ahead and get that into linear form because it's not quite in linear form yet. Remember, linear form is y prime plus, I'll use t instead of x now, p of t, y is equal to q of t. So I've got to divide away that t plus 1 to get it in that form. So I'm going to go y prime minus 3 over t plus 1. Y is equal to t over t plus 1. Not going to worry about that initial condition for quite a long time yet, so don't even worry about that. My integrating factor, that's my strategy for all linear differential equations, is e to the integral of p of x, or p of t in this case, dt, which is e to the integral of negative 3 over t plus 1 dt. Remember, I got to include the negative sign when I'm finding the integrating factor. So this is e to the negative 3 dt over t plus 1. If I use a little substitution, u is equal to t plus 1, du is equal to dt. Then I've just got 1 over du over u. So this is e to the negative 3 natural log of u, natural log of t plus 1. And so this is e to the natural log of t plus 1 raised to the negative 3 power. And so that's, now I can cancel my e and my natural log. So that's t plus 1 to the negative 3. So t plus 1 to the negative 3, which is just 1 over t plus 1 cubed. Now the point of that integrating factor is that you got to multiply it by both sides of the differential equation. So if I multiply that by both sides of this form of the differential equation, I get 1 over t plus 1 cubed times y prime minus 3 over t plus 1 to the 4th times y is equal to t over, it looks like I'm going to get t plus 1 to the 4th. T plus 1 to the 4th. And the point of that is that this left-hand side is always equal to the integrating factor times y if you took their derivative using the product rule. It's always a good exercise to check whether that left-hand side really is the derivative of I of t times y. Because it's a derivative, what we can do is integrate both sides, and so we'll get I of t times y is equal to the integral of t over t plus 1 to the 4th dt. And my I of t, remember, was 1 over t plus 1 cubed. So 1 over t plus 1 cubed times y is equal to the integral of t over t plus 1 to the 4th dt. Now I have to solve that integral, and that looks a little bit unpleasant. There's a nice little trick you can do here, which is a little u substitution. U is equal to t plus 1, and then du will just be equal to dt. And I see I'm going to have a t in the numerator that I have to deal with. That'll be, t is u minus 1 if I just solve my substitution for u. So this is equal to the integral of u times u minus 1 times du all over u to the 4th. And so I can separate that out into u over u to the 4th, which is u to the negative 3, minus u to the negative 4 du. And now I can integrate using the power rule. The integral of u to the n du, learned this back in first semester calculus, is u to the n plus 1 over n plus 1. And so if n is negative 3, n plus 1 is negative 2. So this is u to the negative 2 divided by negative 2. Now n is negative 4, so u to the negative 3 divided by negative 3. Now, I just did the integration. Now is the step when I have to add the arbitrary constant. Not sooner, not later. It's got to be right now. So plus c here. And so if I turn that back into t plus 1, I'm going to pull this negative 2 out and make it negative 1/2 t plus 1 to the negative 2 plus 1/3 t plus 1 to the negative 3 plus c. And this was all equal to 1 over t plus 1 cubed times y. And now I want to solve for y, so I'm going to multiply both sides by t plus 1 cubed. T plus 1 cubed on both sides here. And so on the left I'll get y is equal to, on the right, negative 1/2. Negative 2 plus 3 is just 1, so t plus 1. Plus 1/3. T plus 1 to the negative 3 times t plus 1 cubed is just 1. Plus c times t plus 1 cubed. So I'm going to keep going with this on the next slide so we can solve for the constant. But let me remind you what we did on this slide. I had to get it into this generic linear equation form, which means I had to get rid of this coefficient of t plus 1. So I divided both sides by t plus 1. And so this was my new form of the differential equation. And then I looked at whatever was in front of the y, and I called that p of t. I've got to integrate that, so I've got to integrate negative 3 over t plus 1. So that's easy with a little u substitution. U equals t plus 1. So I get negative 3 natural log of u, natural log of t plus 1. And before I can cancel my e and my natural log, I have to take that negative 3 and turn it into an exponent. Then I can cancel the e and the natural log, and I get t plus 1 to the negative 3, or 1 over t plus 1 cubed. I multiply that by both sides. So I took that 1 over t plus 1 cubed, and I multiplied that by both sides here, 1 over t plus 1 cubed. And that's how I got this line here, 1 over t plus 1 cubed y prime, 3 over t plus 1 to the 4th y, and t over t plus 1 to the 4th. The point of that integrating factor, this is always true for all linear differential equations, is that the left-hand side turns into the derivative of a product. It's the derivative of the integrating factor times y. The right-hand side, you never know what it's going to turn into. But when we integrate to undo that derivative, we get the integral of the right-hand side, t over t plus 1 to the 4th. So the I of t is 1 over t plus 1 cubed. And on the right-hand side, I've got to integrate t over t plus 1 to the 4th. My clever idea there is to use u equals t plus 1 and du equals dt. Plug that in for a u here. Plug u minus 1 in for t. And so that now separates out into two nice powers of u. Well, fairly nice powers of u. They are negative. And so I just remembered the power rule from Calculus 1 here. And so I plug that in with n equals negative 3. N equals negative 3, and n equals negative 2 on the right. And that was the step where I did my integration, so I have to add a plus c right at that step. And then I changed my u's back to t plus 1s, and I just brought this down 1 over t plus 1 cubed times y. In order to solve that, I multiplied both sides by t plus 1 cubed, and so that's how on the right I got negative 1/2 t plus 1 to the positive 1, and 1/3 t plus 1 to the 0, and c times t plus 1 cubed. So we're not done with this yet because we have not yet incorporated the initial condition. What I'm going to do is take this equation over onto the next slide, and we're going to use it to solve the initial condition, and then we're going to be done. So let me remind you of the equation that we had on the previous slide. So our solution so far is y is equal to negative 1/2 times t plus 1. This is all from the previous slide. Plus 1/3 plus c times t plus 1 cubed. And now I'm going to use my initial condition. Y of 1 is equal to 2. So I plug in 2 for y and 1 for t. So 2 is equal to negative 1/2 times, well, if t is equal to 1, then I'll get a 2 there, plus 1/3, plus c times 2 cubed. And so 2 is equal to negative 1 plus 1/3 plus, looks like it's going to be 8c there. And so if I move that negative 1 over, I get 3 plus 3 is equal to 1/3 plus 8c, 1/3 plus 8c. And if I move that 1/3 over, 3 is 9/3. So 3 minus 1/3 is 8/3. is equal to 8c, and I see that I'm going to get c is equal to 1/3. And so I take that c equals 1/3 and I plug it back into my general solution. And so I get y is equal to -1/2 times t plus 1 plus 1/3 plus 1/3 times t plus 1 cubed. And I could do some algebra here. I could maybe expand out t plus 1 cubed, maybe expand out -1/2 t plus 1. I don't think it's going to get dramatically better, so I'm just going to leave it in that form. I have figured out what my arbitrary constant is, so I have solved this as far as it's really useful to go. So let me remind you of the steps here. This came from the previous slide. This was our solution from the previous slide. But it wasn't a complete solution yet because we had not incorporated the initial condition. And we used the initial condition to find the value of the arbitrary constant c. So I'm plugging in, from here I get y equals 2, and from here I get t equals 1. So I plugged in y equals 2 there, and t equals 1 in here and here. So that's why my t plus 1's turned into 2's. And that simplified to -1, 1/3. This turned 2 cubed is 8, and then I just did a little algebra to simplify it down and figure out that c was 1/3. And then I take that and plug it back into the general solution. So that's where I got this 1/3, not this 1/3, but that's where I got this 1/3 in the general solution. It's the value of the arbitrary constant. And so my whole thing turns into just the general solution with the arbitrary constant given the value of 1/3. So in example 6, we're going to find the general solution to the following differential equation. Xy prime plus 3y is equal to cosine x, with x being positive here. So again, that's going to be a linear differential equation, but we need to do some manipulations to get it into the right form. Remember, the form for a linear differential equation is y prime plus p of x y is equal to q of x. In particular, there's not any coefficient in front of the y prime, which is what we have here. So I'm going to divide that away to start. So y prime plus 3 over x y is equal to cosine x over x. Now that's why we were given the condition x is positive. It allows me to divide by x. I don't have to worry about dividing by 0 there. That's really all we use that condition for. So now I'm going to use my integrating factor strategy for differential equations, for linear equations. My I of x is equal to e to the integral of p of x dx. And so my p of x is whatever is in front of the y. That's the p of x right there. So in this case, the p of x is positive 3 over x. So I get e to the integral of 3 over x dx. And so this is e to the, well, the integral of 3 over x is just 3 natural log of x. Remember, I don't need to add plus c when I'm just finding the integrating factor. So I can't, a lot of people would like to say, oh, that's 3x because it's e to the 3 log x. Not true. You can't cancel e and natural log until you get rid of that 3 in between them. So I'm going to make that into an exponent on the x, e to the natural log of x cubed. And so this is just x cubed. And so what you do with that integrating factor is you multiply both sides by whatever you got. So I'm going to multiply both sides by x cubed, and I'm going to get x cubed y prime plus 3 over x times x cubed is 3x squared y is equal to x squared times cosine x. Now, the point of using that integrating factor is that the left-hand side is supposed to look like a derivative. In this case, it looks like the derivative of x cubed times y. The reason for that is because if you expanded out the derivative of x cubed times y using the product rule, you get x cubed times the derivative of the y plus y times the derivative of x cubed. So it really does check there. It's always a good strategy to check when you're at this step in any linear differential equation. because what it does is it just makes sure that you did all the previous work right, and it's really easy to make mistakes through this process. So it's good to check and make sure that the derivative of x cubed y really is equal to what you had on the left-hand side. In this case, it does work. This is still equal to x squared cosine x. And in order to undo that derivative, we want to take the integral of both sides. So we'll get x cubed y, the integral of the derivative is just the original thing, is equal to x squared cosine x, or the integral of x squared cosine x dx. And in order to integrate that, I have to use parts, and I'm going to use my tabular integration trick that I taught you back in the Calculus BC lectures here on Educator.com. You can look this up in those lectures if you like. Remember, the trick is to take derivatives of the left-hand side until you get to 0. So the derivative of x squared is 2x, derivative of 2x is 2, derivative of 2 is 0. And then you take integrals of the right-hand side. So the integral of cosine x is sine x, sine x. The integral of sine x is negative cosine x. The integral of negative cosine x is negative sine x. And then I cross multiply down these diagonals, and I put alternating signs, plus, minus, plus. And so I'm ready to write the answer to my integral. It means you multiply down these diagonal lines. So you get x squared sine x plus 2x cosine x minus 2 sine x. Now, I just did my integral. Now is the time to add my arbitrary constant. Very key that you add it at this time. And the reason is because we still haven't finished solving for y. And as we solve for y, we're going to do some algebraic manipulations, and the c is going to get tangled up in their algebraic manipulations. And you have to let it get tangled up in those algebraic manipulations because, well, otherwise it's the wrong answer. So in this case, to solve for y, I'm going to divide both sides by x cubed. So I get y is equal to x squared sine x plus 2. Looks like I made a small mistake there. I forgot to write down that x. So it's actually 2x cosine x, 2x cosine x, 2x cosine x, minus 2 sine x, plus c. And that's all divided by x cubed, because I was trying to get rid of that x cubed on the left-hand side. So that's as far as I can take it for this one. The reason is because that I don't have an initial condition. All I have is the differential equation. So if I had an initial condition, I would use that to find the constant. I would use it at this step. Let me write that down. You would use the initial condition. Initial condition. If it's given to you. If given, to find the value of c, and then you could narrow that c down to a particular number if you have that initial condition. But in this case, we didn't have an initial condition, so we just stop here with our general solution. General solution. General solution means it has an arbitrary constant in the answer. So let me recap the steps here. I was remembering my generic form for a linear differential equation. It doesn't have anything in front of the y prime. Not a 0 there. Let me not suggest that that's supposed to be a 0. But it just doesn't have anything there. So it's like it's multiplied by 1. But in this case, we have an x in front of the y prime. So the first thing I have to do right away is divide everything by x. So I divide this x away, at least away from the y prime term. That means it shows up in the denominator over here, 3 over x and cosine x over x. And now I can use my generic solution method for linear differential equations, which is to use the integrating factor, which is e to the integral of p of x, and that p of x is the 3 over x. It's whatever in front of the y. If there's a negative sign, you got to include that as well, but in this case there's no negative sign. So we have e to the integral of 3 over x. Well, the integral of 3 over x is 3 natural log of x, and before I can cancel the natural log, I have to move that 3 over to be an exponent, so I get x cubed, or e to the natural log of x cubed, but the e and natural log, now they do cancel, so I get x cubed. So I take that and I multiply that by both sides of the equation. And so that's how I get x cubed y prime plus 3x squared y is equal to x squared cosine x. And the point of that is that left-hand side is the derivative using the product rule of x cubed y. Really using the product rule there. And so because it's a derivative of something, I can integrate both sides. Integral of x cubed y prime is just equal to x cubed y. And on the right I have the integral of x squared cosine x, which is a little nasty. I'm going to need integration by parts by that. But I have my little tabular method that I learned back in the Calculus 2 lectures here on Educator.com, Calculus 2 or Calculus BC. So here's my tabular integration method. I'm taking derivatives of x squared. So I got down to 2x and then 2 and then 0. And then I'm taking integrals of cosine x. So the integral of cosine is sine. The integral of that is negative cosine. The integral of that is negative sine. Then I multiply down these diagonal lines, attaching alternating signs as I do it. So multiplying alternating signs on. So I get x squared sine x. I see I have two negatives here. So that gives me positive 2x cosine x. And then minus 2 sine x. And it's very important that you add the constant when you do the integration, which is right now. So I put a constant on there. And then because I had x cubed y, I wanted to solve for y. So I just divided that x cubed into the denominator there. And if I had an initial condition, I would use that to find the constant. But since I don't, I just stop here and I present my general solution to my differential equation. So that's the end of this lecture on linear differential equations. We've got a whole lot more really interesting material to cover in differential equations. This is just the beginning of the topic. I hope you'll stick around and sign up to see the other lectures on differential equations. We're going to talk about separable differential equations in the next lecture, and then we're going to get into all kinds of other topics. Systems of differential equations, partial differential equations, second-order differential equations. We're going to graph slope fields and direction fields. So there's all kinds of exciting material for us to explore together, and I really hope you'll be part of it. In the meantime, my name is Will Murray, and you are watching the Differential Equations lectures on Educator.com. Thanks for joining us. Bye-bye.